All right, this topic is a different thing in two-dimensional kinematics. We're not going to use the relative motion directly on this. Instead, we're going to talk about what happens when things are thrown through the air at an angle rather than simply up and down. For our purposes, anything that moves in free fall in 2 dimensions is called a projectile. The terminology comes from artillery, and a lot of our other words are going to come from artillery because of the historical import of artillery in the derivation of these results. Here I'm going to show a video where these 2 balls are released at the same time. The left one will be simply dropped. The right one will be shot with velocity start off entirely horizontal. I want you to pause the video and think about anything special that you notice about their motion. The point there, noticing that the rod pulls away and the ball simply drops. But the same rod pushes this one, so it launches moving only to the right. They're at the same height and it's been leveled. So now Alan is going to fire the 2 of them. Observe what happens. Alright, so hopefully what you noticed that was most important is that the 2 balls, which are guaranteed to have been launched at the same time, also hit the floor at the same time. You can hear it even in the way it bangs when it hits the floor. So they fall through the same distance in the same amount of time. This is a different version of the same experiment. Notice that the 2 balls are always at the same height. So if we look here, wherever the red ball is, the yellow ball is at the same height, right? Launched at the same time, falls through the same height. But that means that no matter what time you pick, they fall in the same distance. That implies their average velocity is always the same. And that is only possible if their vertical acceleration is always the same. So the acceleration of the red ball, which we know is g downwards, must also be the acceleration of the yellow ball. They both accelerate downward at g, even though one of them is moving to the side and the other is not. Technically, we only show that the vertical components are the same. What about the horizontal motion of the yellow ball after being fired? So we're going to do a different video here where a professor fires a ball straight up and we see what happens.
So here's the golf ball. I'm going to fire the gun now. Close. Close. Reasonably close. Well, since it's only reasonably close, perhaps perhaps it would help if we give it a little bit of leeway. There goes the gun. Here comes the ball. And this is just in case. Tape it down. So as I'm going to push this now, give it a push. The gun will be triggered when the middle of the car is here. You've seen how high that ball goes, so that ball will go. And depending upon how hard I push it, they may meet here or they may meet there. You ready for this? You ready? I'm ready. Physics works. See you Wednesday.
These presenters are always kind of amazed physics works, which is maybe telling, but it does work. That the ball moving up has a sideways motion which was coming from the cart, and it just maintains that same sideways motion as the cart, even as it gets fired straight up, because the cart doesn't push it to the side anymore. And so it moves with that same speed, and goes in an arc and lands exactly where it had been going. This does actually connect to our relative motion stuff, because if you remember the case of with the Mythbusters clip where they fired a cannon that fires a cannonball at 60 miles an hour out of the back of a car going at 60 miles an hour, and relative to the ground, the cannonball just kind of hung there in space, but it didn't really hang there in space. It was not moving left or right, but it fell. And it fell like any other object that had been dropped. So it has to be sort of in these conditions that they move at constant velocity to the side, because we can just shift to that reference frame. We could have walked alongside the cart, and in that case, the ball would have had no sideways motion, so it would have gone up and down in our reference frame. All right, it turns out that the horizontal motion is at constant velocity. That is, the acceleration of any object, any projectile fired at any angle, is entirely vertical. Let's be careful here. The acceleration is entirely vertical. The motion can be in all directions. And the acceleration is in fact g downward, just like an object that was dropped or tossed. The vertical and horizontal motions do not influence each other. They're independent. Horizontally, the projectile travels at a constant velocity, and vertically, the projectile acts like an object that's been dropped or maybe tossed. So let's see how that sank in. Take a look at this problem, pause the video, come up with an answer, and then we'll talk about it. Two toy trucks roll off the ends of identical tables. The speeds and masses of the trucks are given. The mass is this stuff, 500 grams or 800 grams. We haven't talked about mass, so you can safely assume it doesn't matter in this problem. And they want to know, will truck A be in the air for a longer time, a shorter time, or the same time as truck B before reaching the floor? Well, we see that they fall through the same vertical distance, through the same 30 centimeters. So we know that this is as if we had dropped this from 30 centimeters, because we know the sideways motion doesn't influence how long it's in the air. And likewise, this is if we had dropped it also from 30 centimeters. And again, it doesn't really matter how long it's in the air. So if dropped from rest, we know they both would take the same amount of time to hit the ground. So even though they're moving, they take the same amount of time to hit the ground. So the answer should be the same time. Caveat, real world stuff, the sort of thing an engineer brain talks about. A real toy truck would tumble as it went off the edge because these wheels leave first. So it's a little bit more complicated because it depends on whether they have enough time to rotate through. We're not going to tackle that in this class for a very long time. So right now we're pretending that these are just dots that move off the table. All right, a rock is tossed from the top of a cliff with a velocity that's entirely horizontal. Sketch the time graphs for the horizontal and vertical components of the velocity. So take a second and do that. All right, well, we know that it starts off with a horizontal velocity because they tell us that. So it should have some initial Vx. But it's entirely horizontal, so it should have no Vy. It's not moving up or down at the start. It's just moving to the side. And then as time goes on, the horizontal speed doesn't change because there's no acceleration horizontally, so this should be a horizontal line. Whereas we know that the vertical velocity gets faster and faster. The object gets faster and faster, but in the downward direction. So, whoops, that was pretty bad. It should be a line whose slope is minus g. All right. Next time, we'll talk about using these things numerically and predicting where things will fall.